Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Vision, and is most well known in the work of modeling humans from images. Let's go.
So what I'd like to do today is to present some of the activities in our lab, so mainly in the area of human modeling. And of course, I probably don't need to explain to you why modeling human might be important, since you're apparently monopolizing SIGGRAPH papers. You know that counts a lot as far as all the media and entertainment technologies, but it's also important in many other areas. Like, for example, medicine and sports, where you want to be able to capture the motion of people in a quantitative fashion. You want to be able to measure what they do. What is this patient doing? How is he walking? Why is he limping? That sort of things. It also has many potential applications in the area of smart interfaces. I still have to click on my keyboard, but pretty soon I should be able to wave in front of my computer and have it understand what it is I want. And the last item here seems to be all the rage these days is homeland security, right, and surveillance and all the good stuff that go with it. And so, oops. Oh. I must have said something bad. So, I don't think we will be out of a job anytime soon. And especially given the fact that these days cameras are worth nothing. They are available. You find them everywhere. They're cheap. So that's the good news. I mean, there's a lot of video data available, but the bad news, of course, as we all know, is that data is very noisy. It's getting out some good information, some good quantitative information out of it is a hard problem. And our particular tack in trying to overcome this problem is to throw increasingly sophisticated 3D model at this data, to try to overcome the ambiguity and get out of it some interesting data. And I'm going to talk about this in three different contexts. The first is real-time tracking and detection of 3D objects that usually are rigid. Then we'll move to head modeling, which is not rigid but doesn't deform that much either. And we'll finish by talking about what we do about body modeling, where you really cannot ignore the fact that they are articulated. So in terms of detection and tracking, here's a little example of the kind of things we do. In the center of the image, you have a wireframe, which is a generic model of the face, which actually is not the face of that particular guy. And what the system is going to do in real time is find where the face is and then follow it in 3D. And you can see that it keeps on tracking, even though the guy is doing some very large motion. There are occlusions. And what we're doing here is adding the glasses and the mustache just to show that we really have the 3D position. And he hides half of his face, the system loses the face, and then it recovers, because it has some capability to redetect quickly.
And the model?
This model cannot deform. So here it is a rigid model, but of course, adding the deformation wouldn't be that much of a, it's a few more degrees of freedom. Depends how fine you want to be.
Like, for example, you might be opening a mouth or smiling or frowning or something, right? So that's what degrees of freedom.
Right. If you want to do it to, I mean, you could start with a few degrees of freedom to get some basic motion. And of course, if you want to get the full thing, you need to add all the others. But the formalism itself would probably support that, although we haven't done it. So what you've just seen is based on what it does. It finds interest points, and it matches interest points across frames, so that's, in that sense, it's very traditional. But where it gets its robustness from is from the fact that it matches not only with previous images, but also with a few keyframes. So for example, in the face example, the frontal view is used as a keyframe, the first view. And so when it matches, it always matches against that keyframe if it can. And it gets robustness from that, and it gets precision from the short baseline matching with the previous frames, and it combines that. And as a result, what we have is something that is truly real-time, and that doesn't either drift or jitter, which for the kind of applications we are looking at, which are augmented reality applications, is really important. So here's another example with a sequence from the movie Run, Lola, Run. And that's, so Xing was remarking that he sees that movie very often, and the reason is because we had a joint project with Andrew Zisserman, and he really likes her. So that's the one. And so what's happening is the system detects her, and when she's present, it adds the glasses, and it adds them at the right place. Even though what we're going to see at the very end of the sequence, for example, here she's turning her head quite a bit, and it still tracks.
What features is it tracking?
So in the Lola example, it was really interest points detected by a Harris corner detector. So very simple features. And on the face, for example, it's good enough. It works. There's enough texture on the skin for this to work correctly. Now, if we move to something like this, which is a corridor in a lab, features are not quite enough anymore. They're not, I mean, it's too textureless. So what we've done to overcome that problem is to have it track not only features, but also edges, which are shown in green here. So now it's tracking both interest points and edges, and we are walking, we have our handheld, we are walking through the corridor. It's tracking the thing, and it's tracking it well enough so that we can add this virtual plant. And what's interesting about it is the fact that it's not moving with respect to the ground. It is solidly attached to what it should be, which indicates that the tracking is probably reasonably precise.
Is the camera calibrated?
The camera is, it's not really, we are assuming a focal length, which is roughly correct. We're not trying to compute the implicit parameters. And experimentally, what we've noticed is, as long as the focal length is reasonable, it works. So this is our attempt at going into space. So always same thing, we have a little model of that toy shuttle. We can track it, and because we can track it, we can remove the background, because we know where it is, and we can send it to space. And you can see the hand of the guy holding it, but that's something we should fix. Okay, so what you've seen so far was a tracking algorithm. And anybody who's done tracking knows that sooner or later, no matter what I'm showing, you lose track. If only because the object you're tracking moves out of focus, moves out of the field of view, and then your thing dies. So what you need to be able to do is not only to track, but actually to detect. And this is a slightly different video in which we are treating every single frame independently. And what we want to show is that we can detect the book in real time. Which is what's happening. Again, it's based on this idea of feature points. A little, the colored line that you see are correspondences that it is establishing. And so that's the thing we showed at CDPR. And what's interesting about it is the fact that this time you can actually do detection at frame rate. And this is based on what we call view sets. And what the view set is, it is given a particular interest point, such as the one that is shown here, what you're going to generate is a set of all the not all, but a reasonable sampling of all the possible appearances of that interest point. And in this case, if you, for example, if you assume that the surface is locally planar, you can do that by a fine deformation of that little patch. Once you get all these small images, you can use classification techniques to build a database that is then going to allow you to answer the following question. If I get now a new interest point from an input image, could that interest point in its appearance be the one I've modeled here? And it turns out that if you use this representation, you can do that by a simple decision tree. And very quickly you can answer this question, have I already seen this feature point? Is it in my database? And that's exactly what the thing was doing. So for each interest point it detects in the input image, it assigns it or not to a data point in the database, and then use standard pose estimation techniques to find where the object is. And that actually works for the book, but it also works for non-planar objects such as a face. And since, as we know, I don't have any Stanford rabbit, but I do have the teapot, you can then incorporate it in a tracker so that when you hide the target object, which is the T box in this case, it will know that it doesn't see it and recover when it becomes visible again. So that's one of the important components into a complete tracking system. So you can see the teapot remains positioned reasonably well. And this is a different example where we turn an old projector into a slot machine. Okay, so that was what we do with rigid objects. So here there has been no deformation at all. The next step in some sense is to go something that's a little bit more deformable, which is faces. And of course, faces are a very dangerous topic to be talking about, since, especially in the graphics literature, they have such beautiful results. I was very, I did go to SIGGRAPH last year. And I attended the graphic sketch about the matrix, which was very interesting. But one thing that's remarkable about it is their results are awesome. But they did explain that they took plaster casts of the actor faces, they scanned them, they did an enormous amount of, there was an enormous amount of labor that went into those beautiful results. And if you try to get good results for...
So I just saw them present. I was at a Faces workshop after SIGGRAPH, and they described the whole process. And one comment they made is that like every 30 frames they had to manually go in and touch up. They had a passive system with like 6 HD TV cameras surrounding a face, blasting it with light and so on. And they're using basically optical flow and stereo to try and reconstruct a model with extramats and so on. And they had to go in and kind of reinitialize it every 30 frames. And so it was quite manual. Anyway, just thought I'd add that in there in support of what you're trying to say.
And so if you try to do that sort of thing, not with this beautiful system that they have, but with just ordinary video sequences, or even worse, but this is actually not an ordinary video sequence, but that's a little clip out of the Lola movie where half our face is in shadow. Well, that happens. Or even worse, this is a very short clip from Key Largo, and how we got that by this was pre-DVD day. So we went to the film archive in Geneva, got the celluloid film, and digitized a few frames of that. And that's what this is. And here you have everything. You have, it's grainy, there are shadows, there are specularities. I mean, that's what you have in real data that's not been acquired for special purposes. So if you want to reconstruct interesting shapes from that, you actually have to work at it to overcome all these problems. And just to give you a notion of what a normal vision-based algorithm would do on this. This is the result of running a max flow graph cut algorithm on this data. And I chose this one because, at least according to Rick, this is the best there is.
So you computed?
I registered the image. I have 5 images. I computed, we did a bundle adjustment on the 5 images to compute calibration matrices. And once you have that, you can throw that into the, we use Sébastien Roy's code, and that's what it produces. So of course, I'm being mean. I mean, I have other images where the faces, the shading is good, the lighting is Lambertian and everything, and then the results are beautiful. But of course, that's not the ones you necessarily see at SIGGRAPH or even vision papers. They don't show these ones for a reason.
Is it because the flow is wrong? Because the lighting?
It's really what I think what creates the problems is, okay, these are actually small images. I think this is 200, that's 128 over 200. Because we didn't have an image where he was, we just got that out of the frame of the movie, so Bogart is not the whole image. Then there is a massive circularity here, and there's shadow on the side of the face. And it's amazing, actually, when you start looking at just regular imagery, that stuff happens all the time. So one way out of this mess is to use a model, like a strong prior of what it is you're looking at. So I think last time I talked here, I did present some stuff by using a mesh model and a bundle adjustment technique. And I think what I said at the time was, this did give decent results, but it would work better if you had a better prior in the form of a bare face model, which is what I'm trying. It took about 3 years to actually get the model, but we finally got it, and the model we're using is the one that has been developed by Thomas Vedder initially. I mean, it was first presented in '99, I think. And what this is a model where a face is represented as an average face plus a weighted sum of deformation. So what these S vectors represent here are the 3D coordinates of the vertices of the meshes that represent this stuff. So there are about, I think, 90,000 vertices in one of these meshes, but it's parametrized in terms of only 99 PCA components. And actually, this is only half of the Vera model. In the original SIGGRAPH paper, there was also a texture component. And you can use it, but again, you have this. It was extremely nice to have this texture component because they got very nice results out of single images. But the price you pay for that is, again, you are assuming that the lighting is fairly decent. Because if it isn't, the idea that you're going to get the same color in all images is just not true. So instead of using this texture component, what we are going to do is use only the shape and then exploit the fact that we have a video. So we have several images in which we can do something like this. Given one of the images, which actually doesn't have to be the frontal view, you pick the one that's most convenient, it's fairly simple to roughly register the model so that it projects about where it should. It doesn't need to be very precise. It just needs to be good enough so that the vertices of the model project approximately on the face. Having done that, what you can do is use correlation-based techniques to establish correspondences between the projection of the model, the projections of the model into the other images, which are these points here. And they're actually mostly correct with some mistakes, like this one. And once you've done that, you can formulate the problem of recovering the exact shape of the face in terms of a very simple optimization problem. Because if this point here is one of the yellow dots I showed you. You have established correspondences into the neighboring images, which is what this dotted line represents. But you can also say that if this point really belongs to the face, you can back project it to the 3D model and then reproject it into the image. And ideally, these 2 points should be the same, which means you can write an objective function by saying you're going to try to minimize the sum of the square of these errors, which actually is somewhat similar to a lot of the things that the EU has done a while ago. The difference here is that we actually don't have any type points, for example. We don't have any reference frame, because all frames can play similar roles, and you do that in all the images, and you optimize in terms of these 99 PCA coefficients. And what you get for using, for example, 7 images is this. And as usual, when you show something without a texture, it's unlikely that you would recognize me by just looking at that. Yet, if you look at the actual metric accuracy, it's pretty good. We have a Minolta scanner, so I have also a scan of my face, and I compared it against that, and it's actually quite accurate. The median error is very small, and it's not clear. That's always the problem with who knows who's right. Is the Minolta scanner perfectly accurate? Probably not, because there are spikes also on the scan. So that number is actually a pretty reasonable one.
So you tried texturing one of the scans and projecting onto the other?
Yeah, I have. And then maybe we have a different philosophy. That's why I have trouble getting into SIGGRAPH. Is, to me, retexture mapping is cheating. Because of course it's going to look good.
Well, I was just trying to see, you just claim that the shape is correct, that if you texture map, say, the middle one, and you project...
Oh, okay. Oh, yes. Sorry. Yeah, I have done that, and it's actually, if you want to, I have some results which I might even be able to show you. I'll show you afterwards. But what we've done is, yes, you take this one, and you texture map it in this position. You create the image. These two images are very, very, very close. So you flip back and forth between the two images, and it's really good. Does that answer the question? Yes. And I'll show you after the talk, because I have it somewhere on my...
All right, could you try fitting to the Minolta data? That would seem to be kind of, your PCA model to the, in the end, you...
fitting the PCA model to the Minolta data.
You reconstruct actually a linear comment. Is it expressed in the PCA basis?
Right.
And if so, then you could just fit it to the Minolta, and that's sort of the best you could do. Actually, I would argue the Minolta is probably quite good, ignoring the spikes and so on. So that might give you a sense of how, that would tell you the difference, at least between sort of, how well you fit versus how well you could possibly fit.
Right.
The PCA, gets you to 0.5 millimeter, and you've done the best you can.
Right. Yeah, that would be something to try, and we haven't done. One open question, of course, is how generic is that database? Does it work for all people? Probably not.
So Volker was actually also at this workshop, and I was quite surprised that he was arguing that it was pretty good across ethnicities, even though it was a fairly narrow sampling. He said that anecdotally. Well, no, he showed some results that were suggestive anyway. It's surprising. It might be pretty good anyway, but I don't know.
Well, this one we'll be using is the one that has been done at the University of Florida.
I see.
And so because it was done in the States, it probably was a little bit broader than the initial one they did in Germany.
Right.
But I think the question is valid, and also it's probably its age also.
Yeah.
So actually, when my face can't be fitted anymore by this database, I start getting worried.
Right. Right. But 0.5 millimeter seems really good.
And as far as so here's what we get for the data for for Humphrey. And so in this case, actually, we texture mapped one of the images. We didn't try to work too hard at it. And since Volker had already done the hat, we had to do something else. And the something else was to add back the cigarette. And of course, the point of having the 3D model is the cigarette can cast a shadow at the right place, which is one of the nice things about such things.
Then a related question, have you tried Volker's direct method for single image computation of the face?
Okay, so we've been in touch with, it's not Volker anymore, it's another Vader student who's more recently, his name escapes me. Yes, we tried, and then of course he's run he's run his thing on a few of these images. And then we have the problem of ground truth. He hasn't run it on I should actually send in mine, because the one for which I have a scan, and get what it does.
Right, see how well it does. But I don't know, it seems that one's much more complicated. You have to render the model, and there's more initialization, and probably, and anyway, having the multi-view stereo seems like a good way to go.
But again, this is a single video, right? The point was it's multi-view stereo, but a single camera. And one of the things it computes as a byproduct is the actual camera motion. So it does the model adjustment as it does its thing. And of course, in the case of Lola, we can also, while we're at it, because we've reconstructed the face and we've fitted the motion, we can actually get stereo data for the shoulders, since they appear in the previous sequence, and reconstruct the shoulder and do some simple forms of animation. Okay, so that was what we've been doing with faces. And then I'm coming to what we're trying to do with bodies, where really this time it's really articulated, we can't ignore the fact. And a lot of the things that we've been doing is with 2 or more video sequences, typically acquired by the digiclots, from which we can get stereo data using a very simple correlation technique, and extract silhouettes. Actually, in this context, both are important, because if you have only 2 or 3 cameras that are close baseline, so facing the front, you get stereo data. The stereo data you get is very, very shallow. You only get in the front, you get nothing in the back, and you get nothing on the sides either. So that's why the contours actually help quite a lot. And the kind of results we get is something like this. So on the right side, you have one of the videos. On the left side, you have the recovered motion. And it's a fairly complex motion with some real occlusions in it. It's based, what's hiding behind this algorithm is an animation model, where we model the body in terms of an active skeleton, to which we attach volumetric primitives, so metaballs. Each of the volumetric primitive defines a field. These fields are being added, and the skin is a level set of that field. And what we are trying to do in every frame is deform the skeleton so that the skin level set goes through as many of the data points as possible. And the nice thing about this formulation is very simple mathematically, since each ellipsoid is just a 4x4 matrix that allows us to define an algebraic distance of a 3D point to that ellipsoid. You then introduce a non-linearity by taking the exponential of this algebraic distance, and that's the field created by each ellipsoid. And then to get the actual surface, you take all these fields, you add them, and the skin is defined as a level set of that field. The advantage of this formulation is that everything is differentiable. So your distance is differentiable, which it wouldn't be if you used an explicit representation. Because typically when you use explicit representations, you find the closest facet. And that may change over time. So if you do it this way, it's all differentiable, which means, among other things, which means that your optimizer is going to work better because you have gradients and all that stuff. And also, you can easily talk about normals and curvatures, which is useful, for example, if you start talking about silhouettes, because silhouettes are constraints on the normals, so you need to be able to talk about the derivatives of those constraints. So you need at least second derivatives, which this gives you. So the data, the results I've shown you before was done from this. So here are 3 images acquired at the same time. You get a disparity map out of it. And at each frame, you minimize the sum of the square of the algebraic distances of the stereo data to the model. And one additional nice thing about this particular formulation is when you do that sort of computation, you have to compute Jacobians. That's what your optimizer is doing at each iteration. And it turns out that you can use, or you can extend well-known formulas from robotics to compute the derivatives very simply. You don't have to do a whole chain rule for all the joints. You just do the right cross products, and you get your Jacobians very quickly. Which means this, I think, makes it a good candidate. This formulation makes it a good candidate for real-time implementations, if that's what you want.
How do you deal with singularity?
What
For example, do this, right? And it might be difficult because if you're sort of abstract, there can be multiple interpretations.
Right. You can get lost in a case like that. And right now I'm not dealing with it, and I'm going to come to it in a second. Well, the way we're going to deal with them is by essentially forbidding some things that are just not possible, so that it chooses the right option when it has a choice. So here is actually an example of where it mostly works, but not quite. So it's following the upper body motion, but you may have noticed at the very beginning of the sequence, something really weird happened. Now, it just broke his arm. And that's an example of what we have is an optimization problem where we have noisy data. We have a model with lots of degrees of freedom, and it's easy to go wrong in a case like that. Is that the case you have? Okay, so one of the ways we have tried, and are still trying to overcome this problem, is by constraining the problem a bit more, reducing the size of the search space. And one of the obvious things is to try to impose decent join limits. For example, the model, as you saw it, can do this, which no person could do, of course. A real person is more like this. At some point, you can't go any further. And that's something you want to put into your model. And actually, in the case of people, it's even more complicated than that, is what I can do with my elbow is not independent of where my shoulder is. So I can bend my elbow, put my arm, I can't bend it anymore. So the range of my elbow is dependent on the position of my shoulder, which is typically, by the way, when you look at, in most animation systems that I know of, this is not taken into account. Typically, the way this is done is by having, you represent the positions in terms of Euler angles, and you put ranges on the Euler angles, which means essentially that you're assuming that the different degrees of freedom are all independent from one another, which is actually not true in real life. In fact, in real life, they are dependent, and you need to know them. So one reaction, our first reaction was to, okay, well, let's go see medical books. They must have been thinking about these things for a long time. Well, they have, but they don't have the same needs we have. They basically will give you the angles in a couple of planes. They won't give you a complete sampling of when it can and can't be done, can and cannot be done. So what we had to do is actually to go and measure them. So we've been looking fairly carefully at the specific case of the shoulder and elbow, because it's actually, the shoulder is one of the more complicated joint in the whole body. So if you can do this one, you can probably do the others as well. And we have access to a Viken motion capture system. So we asked a number of people, actually 4 in this case, to try to sample everything they could do with their elbow and shoulder. So what we have, they are wearing the black suit with the ping pong balls. We capture the motion, and what you are seeing here is the motion of the shoulder represented in terms of a rotation in quaternion space. So to be precise, this is the imaginary part of the quaternion as the guy moves his arm around. So people have been doing this, and then what this here is, the red dots are the samples, all the position a particular subject has been able to reach. And since we like implicit surfaces, what we've done is to fit an implicit surface to this, so that we have a representation in terms of if some field is negative, it's a permissible position. When it becomes 0, you are at the limit, and when it's positive, you are in an not humanly possible position. And what's nice about this particular way of doing it is that, again, we have a differentiable way of expressing our constraints, which means we can put that into a constraint optimization scheme. So we can turn the previous optimization, which was unconstrained, into a constrained one. And that's also a reason for expressing things in terms of quaternions, because in quaternion space you have a notion of, you have a distance, and therefore you have a notion of orthogonal projection, which is good when you're trying to do that sort of things. So these were the limits for one joint. But as I've said, the limits of different joints are not independent. So in the case of the shoulder and elbow, what we did is, given all the possible, or at least a sampling of all the possible position of the shoulder, we've also sampled the position, the possible position of the elbow, and the elbow has 2 degrees of freedom for our purposes. So this time it's not a volume anymore, it's a surface that can also be represented in implicit terms. So what we do is, for different positions of the arm, we have a representation of the limits of what the elbow can do, and for positions that are intermediate between those sample positions, we interpolate between the 2 surfaces. If it's in shape, it doesn't. But anyway, that gives us a way to express the limits of the elbow as a function of the limits on the shoulder. So that, for example, we can do something like this, which is, this actually is purely animation, where we've asked a graphics designer to make a tennis serve, which is this thing, but she exaggerated on purpose. So this motion actually is not physically possible. You would damage your shoulder and elbows if you try to do this. But what you can do is, given this motion, you can feed the system and project every pose into the permissible space, which gives you something like this, which roughly looks the same, but is now physically possible. And actually, that's a potential application of this particular study, is you could imagine putting this into an animation system where the animator would do the motion any way he likes, without caring about whether it's possible or not, and have the system projected into the realm of possible things. And in terms of motion capture stuff, as I said, the constraints are now expressed in a way that is differentiable. which means we can use well-known robotics techniques, inverse kinematic techniques, to turn our unconstrained optimization problem, the one I showed before, into a constrained one where you're trying to approach the 3D data while enforcing the constraints about joint limits, which helps resolve a number of the ambiguities that you may face. So for example, here we're using the Digiclock data, which is not all that wonderful, and it sort of tracks. The data here is shown as the blue dots. So when you look at it actually like this, it looks like it's tracked fairly reasonably until you actually look at the stuff in 3D. And then you realize that at some point in the model, the recovered motion, I mean, she bent her elbow the wrong way. And she would certainly have, I mean, it's just not possible. If you do the same optimization, but this time with the constraints enforced, you get something like this, which actually tracks a bit better because the search space has been reduced, and more importantly, you get actually all the poses on our possible poses. So that's one way of dealing with ambiguities. Another way is to try to look at motion models, because if you happen to know a priori that the person is going to perform a certain kind of activity, you can use that. And we've been looking at that in the context of walking, jumping, and running. And here we have been using our Digiclocks to try to acquire the data. You may have noticed that all the examples I've shown until now, the person was moving, but they weren't changing position. And the reason for that is because with our stereo setup, we can't get any decent data if the person is moving about the room. That's the limiting factor. And that's what you see here. If we're going to do walking and jumping, well, of course, the person has to move across the room. And the kind of data we get out of our Digiclocks is crumbing. This is something like this. These are the 3D points. A person can more or less detect that something is happening in there. But the system really has trouble now. And again, if you do the unconstrained optimization, you lose very quickly. So the white skeleton does not follow her very well, mainly because of occlusions. So one way to overcome this problem would be to use much better stereo data, like the kind of data you've been using for the break dancers. That would certainly help, because you have front and back, and that would be a lot better. But if you don't have access to that, something you can do is to try to use a motion model. So if you followed the vision literature in the last few years, you've all heard about condensation and all its derivatives and various statistical methods. And I've always had a problem. I'm not very comfortable with statistical techniques. So one of the things we try to do is to do that sort of things, but with deterministic methods. See if we can get a decent result, enforce these motion models in a more deterministic way, which means in a computationally more effective way. And to do this, what we've done is, again, we've asked a bunch of people, in this case 9, to walk, run, and jump. The walking and the running were done on the treadmill, and we observed them with the Viking. And so the walking and the running was done. We asked each subject to walk, I think, from 3 to 7 kilometers an hour, and to run from 6, or I forget the number, but at various speeds that we looked at. For each capture, what we did is for a cycle, you take every position, that's a vector of joint angles, you concatenate those vectors, and that gives you a big long vector that describes the whole motion for a walking or a running cycle, or from start to end of a jump. And then you take all these vectors and you can do just a principal component analysis on them. And what is shown on this slide are the first two components of the PCA decomposition. Every little dot here represents one subject walking or running at a definite speed. And what's sort of interesting about this, these are the walks, these are the runs. And one thing you can notice, even based on the first two components, is all the red dots here are one person. All the blue dots here are a different person, walking at different speeds. So these things cluster by person because they don't all walk the same way. And the other thing that's interesting is it doesn't take very many coefficients to describe a large chunk of the variability of the database. So in practice, when we fit those models to our image data, we don't need to fit all degrees of freedom in each frame. We just are going to fit a few PCA components to a whole walking or running cycle, which means we are going to deal with a problem whose dimensionality is going to be much reduced. So in some sense, it's very similar to what we did for the faces, where a motion is an average motion plus a sum of deviations. And what these data vectors represent is each one represent a set of curves like this, where each curve represents the motion of a particular joint, the angles attached to a particular joint. And also what we need on top of that is a temporal variable, because we normalize time. A motion goes from 0 to 1, and we need a motion variable that tells us where in that cycle we are. So the state vector for our application is this temporal variable plus the weights. That defines the motion over a whole sequence. And if we use stereo data, we can plug this into our earlier objective function so that fitting this model to the stereo data, again, is a simple problem of minimizing the least square sense, where everything is differentiable. So we've reduced it to a simple least squares minimization. And for example, here is an example of tracking a very slow walk. And what's sort of interesting about this example is, in this case, this guy was wearing, you may not see it very well, but he was wearing sensors on his thighs and calves, which weren't used to do the fitting, but were used for validation purposes. And what we get out of the stereo data and what we get out of the sensor is pretty close. A faster walk, so one is a man, the other is a woman. It tracks reasonably. Can run. And one thing also that's interesting about this is once you process a sequence, you get a set of weights, a set of PCA weights. And in the case of the girl you just saw, she was actually part of the database. So we had her motions, each of these red dots corresponds to her motion at a different speed. And the black dots here correspond to the parameters we measured from the stereo data. And these parameters have the good taste to fall right in the middle of her cluster, which means in some sense, at least for a small database, we can recognize her just on the basis of that. So to some extent, it duplicates this human ability that we have, that if you see somebody walking in the distance, even though you may not see their faces, you have an idea of who that might be. And actually, now I'm venturing in waters I'm not terribly used to, but this can also be used for animation purposes. Because we have, let's say we have a person that we observe from our video walking at a certain speed. We can compute those PCA coefficients, and we can then measure the distance of that person to other members of our database. So this person we are seeing on video is not in the database, not in the motion capture database. But we can measure its distance to the other people, and we can say, okay, well, this walk is a weighted average of all these other walks with such and such coefficients. Which means we can now take that walk we just saw and speed it up by taking the sample, these weights we just computed, use samples of the other people walking faster or slower, use the same coefficients, same weights, and synthesize what that person would look like if she walked faster than what we observed. And so the whole idea would be that instead of having to motion capture a person walking at a whole bunch of different speeds, it's enough to capture them walking at a single speed, and synthesizing all the others. So here is what it looks like when you use data from the motion database. So here are just two different women in our database. These have been motion captured. They are two different people, and they run differently. So that's the kind of variability that you encounter when you compare the motion of two different people. Now what we've tried to do is take the motion of a person in the database, speed it up synthetically using the method I just described, and then compare this sped up motion to what we've actually motion captured. And the reason you see only one character in this case is because the superposition is very good. You're going to see that as the motion speeds up more and more, there's a bit more difference. You can see that the arms are not quite right anymore, but still it's very close. And the reason actually probably the arms are not entirely right is because it's a run on a treadmill. And running on a treadmill makes you run slightly differently from what you would do in real life. So this is the same thing with walking, where two different people walk differently, obviously. But now if you... That starts. So now if you capture your motion not from the database, but from the video, what you can do is you've captured the person in video walking at a certain speed, and you speed her up synthetically. And we compare that to the motion we had recorded previously in using motion capture. And you can see that at least as far as the legs are concerned, it's very close. So this is a I think that would be an interesting application if you want to retarget the motion, speed it up, slow it down. And that could be a case where combining this kind of 3D modeling and your appearance-based kind of approaches would make a lot of sense. And you can actually make that a little bit more complicated if you now allow what I've shown so far, where motions at a steady pace. But if you allow the PCA coefficients to vary over time, you can actually allow the capture of a motion that is not steady. Like, for example, here a run at an increasing speed, or here a motion where she is first standing, walking, and then running. And what's interesting about this is not only that it tracks, but also that it knows when it switches from walking to running. So if you wanted to use this to analyze a sporting event, it would, I think, make sense. It's too bad we're we're going to have to wait for the next Olympics, because for this one we missed the boat. But sports are actually a very good application for that sort of stuff, because you know a priori what the people are going to do. You know they're going to run, you know they're going to jump. What you don't know is exactly how they're going to do it. But that you can get from the videos, so that after the fact, you can actually analyze the performance and understand why they did or did not break the record, for example. And of course, I've mentioned that one of the things we want to do is to get better stereo data. That would help us. But the other trend that's highly popular, at least in the vision field, is to do it monocularly. So this is actually fresh off the presses, and we still have to work at it, but this is running the same algorithm, but not on stereo data anymore, on a single monocular sequence, using, again, the idea of the transfer function. And that seems to work reasonably, so that eventually we should be able to do that sort of things using a simple camcorder. And that's one of the goals of this whole thing. And it actually makes sense in terms of applications, and if you talk about sports, pretty soon you're going to talk about either golf or tennis, because that's where the money is. And golf would be an excellent application for that sort of thing. We've actually worked with a small company in Switzerland to make an algorithm that can detect the club. So the idea is you take your laptop, you have your webcam plugged to it, and with that and only that, you can actually model the trajectory of the club. And what you see on those trajectories, actually, they are color-coded to represent the speed. And that's a good start, but what's even more interesting would be to be able to model the position of the body. So, for example, what golf professionals want to know is what was the position of your shoulders or your hips. And this actually, again, is a good application because you know the guy is going to swing. So you could build a motion model of that and get all this information from that sort of video sequence. So to conclude, what we are going to be doing in the future is to try to keep on refining our motion models and our biomedical constraints so that we can increase the robustness of our algorithms, and so that eventually we should be able to work with, ideally, just a simple camcorder that you can take with you on the golf course or anywhere else you want to. And the challenge here, what's hard about this is if you scan the human modeling literature, they are very complex, beautiful, sophisticated models. They exist. But they are so beautiful and so sophisticated that they are not very usable for us. They have too many degrees of freedom. They're too complex. On the other hand, the models we are currently using are still too simple. And the challenge is to find the right balance. And I think that should keep us entertained for a few more years. And I might have a chance one of these days to tell you about it. Thank you.